So last day we have discussed about how we can create a binary search tree. I mean, we have discussed about the programming part of the binary search tree creation. We will take a short tour on actual implementation in using some language very soon. But before that, today we will go for some advanced part of the binary search tree. Now, before going to advanced part, let's clear some points about the binary search tree, about the searching time and all. So the first thing is that how you can define the height of a binary search tree. So the first point is that height, I'm sorry, how you can define this. You see, let's try to realize from an example. Suppose that you are creating a node, say A. This is the level and height of this particular node is h equal to 0, right? Uh, number of node n is equal to, here is equal to 1. If you just add, say, two more node under A and B, I mean under A, since this is a binary search tree, obviously maximum number of node will be 2, and since we are considering the number of node, so let's consider what is the maximum number of node in that particular height. So this is in height 1, and now together total number of node here will be equal to 3. If you extend it more, here height equal to 2, and the total number of node is equal to, you see, 3 plus 4 equal to 7, and so on. Now see, if you want to make a relation among these various heights and number of nodes, you see, we can say that this is number of node of a binary search tree, that number of node of a binary search tree is actually total number of node, I should say, that is, this is, you can say, 2 to the power h plus 1 minus 1, right? Right, total number of nodes is 2 to the power h plus 1 minus 1. So now, um, so this is how you can actually find the, if you know the height of a binary search tree, you can easily find the total number of node possible, maximum number of node is possible. Now question is that if the number of node is given, then how you can find the height, right? Um, you see, if I just try to find that mean, Just a minute. Okay. So, and now question is that how you can define an inverse relation. It's something like n is equal to 2 to the power h plus 1 minus 1, right? And what is the value of log 1? So you see, if we ignore this particular term, you see, and if I take a log between this one, if I ignore this one, I mean, so I can say that it's almost equal to the power h plus 1. And if we ignore this term, and if I take a log among n, obviously the base will be 2. You see, I will find that height can be said as an order of log n, right? Because ultimately I will get h will come here and log 2 will get cancelled because it will be 1. So I can say that height of a binary search tree in order of log n, where n is the number of node, total number of node in the binary search tree. Now, since you have a structure something like this, and your height is order of log n, so naturally the searching time of a binary search tree is also log n. And here is the actually, you know, here the binary search tree is better than other linear data structures, at least for searching time. In a sense that in case of a, if we consider an array or a linked list, there the searching time is generally big of n. It's a linear time, but here the searching time is big of log n. So we can get a benefit for searching data if we store in a binary search tree. But still we have some problem. The problem is that suppose we know that how we can create a binary search tree from a set of numbers. I mean, say, for example, say 10, 2, 15, 5, 8. If this set of numbers is given in this order, then we know that the first one we considered as the root of the tree. So that means first one will be the root, and then 2 will be in this side, then 15 will come, then 5 will be in this side, and maybe 8 will be in this side, something like this, right? And so that means although I don't have lot of I mean all the nodes are filled not filled up with the both child, still we can have a uh, you can say that the still it can follow, sorry, almost the searching time can follow almost sort of in an order of log n. But if we just sort this order, okay, and try to create the tree, then I mean after sorting it will happen something like 2, 5, 8, then 10, 15. And if you try to create the binary search tree in this situation, it will become something like 2 in this side, 5 in this side, 8 side, 10 side, 15. Both are representing same tree, actually same set of data. Not only that, if you take a in-order traversal, both will show the same order. Now difference is that since in this situation basically we have null in all the left side of the node, so you can assume the same situation something like a linear list. Just since all the left part is null for all the nodes, so you can assume easily that okay, I mean uh, the node is basically, there is a one-way connection and it's acting something like a linear list, right? Although there is a provision to go in something to the left. So in this situation, the searching time become a sort of in order of n, right? Although it is in a tree, I mean theoretically you will say the searching time is big O of log n, but still here in this special situation, although it is binary search tree, ultimately the searching time will become big O only n, because there is no branch in any of the node. So this is a problem. Now as a programmer, you don't know or you cannot guarantee that the data will not come in this particular fashion. You cannot guarantee that. So if the data come in an ascending order or descending order, then how we can restrict the binary search tree to grow in a particular direction? That is the point. If we allow the binary search tree to grow in a particular direction, then ultimately my purpose for creating the binary search tree will fail, because my purpose is actually to minimize the searching time. That will fail. So how to do this? That means what actually we have to think about is that suppose we have a node over here, some node x, and this node have some left child and some right child, suppose. I mean not child actually, I must say that a left subtree, and it may have some left right subtree also. This particular node, or still if you add many other nodes, I will say that this particular binary search tree is okay, although all the nodes may not have both children, all the non-leaf nodes may not have both children, still it is still okay. You cannot say that all the nodes actually growing in a particular direction. But this is not true in this situation. So if you take a generic situation something like this, that we have a node, some node at some point of time, maybe it is a root, or maybe the left sub the maybe representing this node as 10, or maybe this node as 2, something. There is a provision something can be in the left and some set of data can be in the right, and this is your left subtree and this is your right subtree. This is what we know. But where we stuck actually, we stuck in a point about the difference between the height of this left subtree and height of the right subtree. So if we consider that height of the left subtree is h1 and height of the right subtree h2, what is h1 minus h2? That matters. If I say that h1 minus h2 is in a particular threshold, I can say that okay, the tree is little bit, it's okay, it's balanced. So a new word come, balanced. So what does balanced tree mean? A balanced tree means the difference between the height of the left subtree and height of the right subtree of the root is in a particular threshold. And that difference is called balance factor. This balance factor should be in a particular threshold. Theoretically, in the literature of binary search tree, this balance factor should be in a range -1, 0 or +1. This -1 and +1 is representing one of them is actually have a one more height than others. This height of the left subtree can be 3, height of the right subtree can be 4. So 3 minus 4 will be equal to -1. In an opposite situation, it will become +1. And 0 means actually you can easily understand the height of the left subtree and right subtree is same. Now this particular tree may not be balanced because I have taken a very arbitrary example. But my point is that till now we have not thought about this balancing of a binary search tree. We always consider a situation will be something like this, or maybe many more. I mean, if we add many data, say 12, 20, and here we have say something like say 4, and here we have something like 1. So naturally, and in between 2 and here we have 4, something like that. So many more nodes will be added. That is not important. Important is that still now we consider always binary search tree looks something like this, but it's not true. Depends on the data set you are getting. You may create a binary search tree something like this, which will actually hamper our target. So if we find that a tree is going to be unbalanced, then what we have to do? We have to balance it properly. So we must have some rule by which we can balance this tree. And the second point is that so question is that now how we can add this extra information balance factor in the node. So the programming point of view I will not consider for today, but theoretically you see that you must have balance factor associated with each and every node. But remember one thing, this balance factor is mean the difference between the height of the left subtree and height of the right subtree, not the difference between balance factor of the left child and balance factor of the right child. So What is balance factor? Some people by mistake calculate balance factor as something like this. Which is going to be entirely wrong computation. If you calculate in this way, balance factor of a node is not related with balance factor of any other node. Node in the higher level. So let's do one thing. Let's calculate a balance factor of a particular node, particular BST. For example, something like this. So if we have a 10, then in this side, if we have 2 as just okay. So let's you don't need to draw this. Let's calculate it from here. You see, and one thing always remember that balance factor calculated, we start calculating balance factor from the bottom to top in this side. Okay, so there is no specific uh, you know you cannot you can calculate from the right, top to bottom also. Okay, but problem is that if it may happen that in a particular tree there is more than one nodes whose balance factor is violating this particular range, and the height of the nodes can be in different, the nodes can be in different level or different height, right? So question is that which node will have to be correct first, right? So always remember that balance factor of the higher level node is actually corrected first, and then balance factor of the lower level node is corrected. We start balancing properly from the leaf node onwards, and then we grow up and we check the root at the end, basically, because it is in lower level. Now okay, so let's calculate the balance factor first of all. Now you see, let's take this leaf nodes. If we have a leaf node, that means something connected with previous nodes in the tree, and there is nothing, it's null and it's also null. Left and right are null, right? So you can say if this is a leaf node, this height of this one is 0, and height of the right subtree is also 0. There is nothing in the left and right. So that means balance factor will be 0. So that means balance factor of all the non-leaf nodes, all the leaf nodes actually are 0. That means blindly you can put 0 in this place, this place, this place, and this place. Fine. Then what about balance factor of 5? You see, the height of the left subtree of 5 is basically 1. Only 1. Right. And height of the right subtree is also 1. There is only 1. So that means Again 1 minus 1, the height of the left and height of the right subtree. So 1 minus 1 is again 0. Now if you calculate a balance factor of 2, then it will be height of the left subtree is 1, but height of the right subtree is what? 2. That is the maximum number of paths to reach to the leaf node from that particular node from 2. So that is 2. That means 1 minus 2. That means minus 1. So balance factor of 2 is minus 1. Still this is in the range, right? Now balance factor of 15 is what? It will be again 0. And balance factor of 10 is what? You see, balance factor of 10 is in the left side we have maximum maybe in this path or maybe in this path, doesn't matter. So 1, 2, 3. And here it is 1, 2 or maybe 1, 2. I mean 2. That means 3 minus 2, that is plus 1. So we can easily calculate, I hope now you can easily calculate the balance factor of every node of a binary search tree. Now question is that if the balance factor is validated, then how we can correct it? So I'm coming it very soon. And this is, if the binary search tree is balanced, then this particular tree is called AVL tree. So we are going to go through a special type of binary search tree. What do you call? AVL tree. Or so you can remember the concept of binary AVL tree as balanced binary search tree. Okay. So if you forget about this balance part, then it's normal binary search tree. It will follow the normal rule of binary search tree. But if you add this one, it become an AVL tree. So that means all the binary search tree is basically an AVL tree. But I'm sorry, all the AVL tree is a binary search tree, but not all the binary search tree is AVL tree. Right? The balance factor is coming in the scenario. Anyway, now let's assume some situation to realize how we can, you know, balance a particular binary search tree if it become unbalanced. So let's take case number 1. Case 1. Well, let's calculate the balance factor once again then. So suppose we have first of all, you see balance factor is equal to height of the left subtree and height of the right subtree, right? So that means if we have a tree something like this, if some data, okay, so there is, suppose that this is a binary search tree, okay, and I want to calculate the balance factor for each and every node. Then you see I will start from this leaf node. You see leaf node has contain actually null in both sides. So basically the height of the left and right subtree for leaf node is 0. So that naturally 0 minus 0 is equal to 0. Then if you calculate the balance factor for node D, it is the height of the left subtree is 1, but basically there is nothing in the right subtree of D. That means height of the right subtree is basically 0. So that means the balance factor for this node D is actually 1 minus 0, right? That is 1 plus 1. Now consider this situation C. Again, the C have something in the left subtree and right subtree is totally blank. That means the height of the left subtree is 1, 2 and height of the right subtree is 0. So that means the difference between these heights is actually 2 minus 0 is minus 2. And similar situation over here. This is a leaf node. So the balance factor of this leaf node will be always 0. And what about this B? This is what you can say balance factor in the, you see, in this case left subtree is totally blank, right subtree has only one node, so height of the right subtree is 1, that means 0 minus 1, that is minus 1. So now what is the balance factor of A? That is height of the left subtree, that is 1, 2, and height of the right subtree is 1, 2, 3, that means 2 minus 3 it will be equal to minus 1. So these are the balance factor associated with each and every node of the binary search tree as an example. And you see, as we have discussed over here, that the height, the balance factor should be in a range minus 1 to plus 1. We can see, we can see that the balance factor is actually violated in this particular node. So somehow we have to correct this node, and how we will correct this node we will see very soon. Okay. Yes.